This chapter, one more chapter, and then the final. So we're coming down the home stretch. We're going to get into the weeds in chapter 8 and 9. The bonding is chock full. So we split it up into 2 chapters and 2 exams as a consequence. We're going to get the general concepts in chapter 8, and they're going to be pretty much historically presented. These are the ideas that came along first, and then we modified them. So here's some questions to consider. What do you mean by a chemical bond? We can simplify it, right? We can simplify it and say things like it's whatever holds 2 atoms together. But when you try to use that definition to make predictions or do any type of calculations, you kind of, there's no way. So we need to know more about the chemical bond. We got to get down in the weeds. And then in the process of determining what a chemical bond is, we also have to consider why do atoms bond together? Why don't they just all stay apart? There has to be something driving them to associate with one another. There must be some sort of, and I think of in these terms, an energy advantage to bonding. And not just why, but how do they do it? Because you can get 2 atoms close to one another or 2 or more atoms, and they may bond a certain way, or they may decide to bond a different way. And we've looked at, I think we've looked at an example of, we've got the same formula for ethanol as we do for dimethyl ether, but we know that they're bonded differently. So why do they do that? And how do they arrive at that configuration? And we're gonna go back all the way to Dalton's atomic theory. He pulled things together. I've mentioned this before. Most scientists tend to approach the world like a chef with a sharp knife. They just chop it up into little pieces and see what they've got. Every once in a while, you get someone come along who has the knack or ability or the drive to take all those little pieces and put them together into a coherent story that we would call a theory. And Dalton was one of them. He proposed the atomic theory in the beginning of the 19th century, and that sort of laid the foundation for understanding how chemicals react with one another. But it didn't go far enough to explaining what drives those atoms to bond or to rearrange. So I guess you could say we're progressing in small steps, baby steps. All right, there's no real simple way to define the chemical bond. I'm going to introduce you to a person here in a minute who seemed to have a pretty good grasp of what the chemical bond was and wrote a book on it and got a Nobel Prize for it. So he impressed a lot of people when he did that. We can look at it as a force that holds atoms together and makes them function as a unit. One thing we do know, that a bond will form if the energy of the aggregate, when they come together, is lower than the energy of the separated atoms. That seems to be an energy advantage. There's another way of putting it. If we look at the chemical reaction, everything that goes into the chemical reaction is a system. Then if the system achieves a lower energy, and it's tending toward the lowest possible energy, That is another force that drives the reactions, drives the formation of chemical bonds and the breaking of others in order to form new ones. If we look at the very simplest interaction between two ions, and our example here is the sodium ion and the chloride ion. The attraction there, the thing that holds them together, what we would call an ionic bond, is purely electrostatic. And there are two things that influence the strength of an electrostatic bond, is the distance between the nuclei, and the size of the charge differences. So if you just got one positive, one negative charge, you get a certain strength of attraction. If you happen to have a 2+ charge and a 2- charge come together, then you'll have a stronger attraction. And then if you have a large positive and negative ions, that will keep their nuclei further apart, and it'll also spread that charge over a greater area. So the charge density decreases, and that decreases the strength of the attraction. But if you can get that charge into a smaller package and get those nuclei closer together, then the distance between them increases the strength of the charge, the attraction, the force of attraction. And this is governed by Coulomb's law. Coulomb was a Frenchman, and he was working with electrostatics during the 1700s, I think, 18th century. And he devised this law. And that box in there is supposed to be a dot, a multiply sign. So what he said was the energy, and the unit would be in joules, the energy of attraction is equal to some proportionality constant. And I don't even have this one memorized. 10 to the minus 19th joules, nanometers. Yeah. And then the variable terms are the charge on one and the charge on the other. Now, these can be either opposite charges for attraction, or they can be the same charges for repulsion. And that will give you an energy value, but the energy value, of course, the sign will be flipped. And then the distance between them. Okay? So that incorporates both the size of the charge and the distance between them in that formula. And we can calculate the energy of attraction between this sodium and this chloride ion using that equation. Right. If we do, we find that the attraction between them is going to be have a negative value because one of these is positive and one's negative. So the energy of attraction has a negative value, and the negative means attraction. Negatives also reference lower energy. The more negative it is, the lower the energy of the system. So that means a stronger attraction will give you a lower energy value overall compared to the separated ions. Okay, so we're going to look at this example. Two hydrogen atoms come together, and we know from past experience that hydrogen is one of those diatomic elements. Right? At room temperature and 1 atmosphere pressure, hydrogen is naturally going to be diatomic, two hydrogen atoms. So if we look at it as two independent hydrogen atoms, neutral atoms approaching one another, they're going to have their identical atoms, so their attractive forces, their attraction of the proton in their nucleus is the same for both of them. All right, so we know from experience that this is going to be a covalent bond. It's going to be a bond where they share electrons. And this picture on the side, which came out of your textbook, shows a probability distribution for electron density. And we find that the electron density, we're going to find the electrons spend most of their time between the atoms. Now, those dots don't tell us exactly where they are, because we know from Heisenberg's uncertainty principle that we can't know that. Not if we want to know anything about the energy, which is where we want to spend most of our time. And effort is in learning the energies of these interactions. What we have to balance is we've got this proton and this proton, which is most of the hydrogen isotopes are just one proton. And then we have the electron out here and the electron out here. So we have two things happening. We've got these two protons, and if we get too close, then the force of repulsion is going to keep them apart. And if we get these two electrons too close together, the force of repulsion is going to keep them apart. But there's also an attractive force between this proton and that electron, well, and this electron too, and this proton and those other electrons. So there's a balance that we're trying to achieve by bringing these two atoms together. This is one way to look at it. You have potential energy on the y-axis, and on the x-axis, you have the distance between the nuclei. The best way to look at this is not to go from left to right, which is the way we normally would read a graph. But if we're forming a bond, start from the right, the separate atoms, and move them closer together from right to left. And we find that the potential energy drops as they get closer together. And it's optimal at a certain distance, 0.074 nanometers. Gives us the optimal distance and a balance between repulsion and attraction. If we try to push them any closer, then those repulsive forces become huge. That's why this steep curve, it goes up like that. So we get the bond length is 0.074 nanometers. And this is also, this can explain why it's so difficult to get hydrogen nuclei to fuse into helium, nuclear reactions. Because you see, as you get closer, the repulsive force goes way up. That's why sustained fusion reactions of hydrogen only occur in stars, because you need very close proximity, very high energies, and high densities to drive those nuclei close enough together so that the strong nuclear force can take over. There are four fundamental physics forces in the universe: electromagnetism, gravity, strong nuclear force, and weak nuclear force. And the strong nuclear force is what would fuse those together if you got them close enough, under enough energy to overcome these repulsions. But since we're in chemistry, we're not going to go there. That was just a freebie. All right. So here's some key ideas in bonding. We have the difference between ionic bonding, where our previous example, sodium and chloride, where an electron was actually transferred from one atom to the other. Now we have a positive charge and a negative charge, and the attraction is purely electrostatic. Then we have atoms that come together and they don't transfer electrons. So the only way they can bond is what we call covalent bonding, where the electrons are shared between the nuclei. And there is an energy advantage to that also. We're going to talk about why and how you decide whether the bonding is probably ionic or whether it's probably covalent in a few minutes. There are intermediate cases. In other words, if you have a covalent bond, it's very likely that there will be some ionic character to it. In other words, electrons will spend more time maybe this direction. All right. So it'll be only a slight negative and a slight positive. That delta is what we mean by slight. It's not a full charge. This is a covalent bond, but the electrons tend to have sharing more density toward one than the other, unless they're exactly the same, and then it's perfectly balanced. And those are the only cases where you have a pure covalent bond. It's where you have two identical elements, the atoms, bonding. If they're different elements, then they're going to have some ionic character, even though they may be covalently bonded. And even ionic bonds, you can look at them also. There are no ionic bonds that don't have some covalent character. So these bonds are on a continuum. All right, we could draw a line like this. This would be 100% ionic. And this would be 100% covalent. And the bond will be somewhere along here. Now, if we do have a covalent bond where you have sharing of electrons, and this is empirically determined. If the separation of charges in a covalent bond is very, very small, then we say that bond is nonpolar. In other words, it doesn't show a significant polarity between the negative side and the positive side. Another way of saying that is equal sharing of electrons, although equals in quotes, because you can have what we consider nonpolar covalent bonds when there's just very slight polarity. Like I said, it's on a continuum. Now, we might, for simplicity, say that there's no charge separation in the bond, but that's hard to prove. I believe there's always some charge separation, even if it's just instantaneous, because these things are not static. Electrons are not static. They're always in motion. The other possibility is a polar covalent bond, in which there's a slight negative charge. There's a separation of charges in the bond itself, an unequal sharing of electrons, and gives you that partial positive and partial negative charge. What that does for the bond is it sets up the possibility for electrostatic attractions. Say if this is only a diatomic compound, and it comes anywhere near another diatomic of the same kind, you have the possibility of that electrostatic interaction. Right? And we'll get into that one in more detail in the second semester. And we can actually measure the polarity of a bond. It's easiest to do if you have just two atoms in the bond, like hydrogen and fluorine is our example here. Right? We put those in the space as a gas in the space between two charged plates. And we can measure the effect they have on the capacitance between those two plates, and then interpret that in terms of what is their polarity. All right. So chemical bond is, in general, can be described as forces that hold groups of atoms together, make them function as a unit. That's a generalized definition. These are the questions that we asked earlier. Why do atoms bond with each other? Atoms bond with each other to form molecules if the energy of the aggregate is lower than the energy of the separated atoms. That's one explanation for why they bond. How do they do this? Well, they either transfer electrons completely from one atom to the next, and then the attraction is purely electrostatic, or they share electrons. That's how they accomplish this lowering of energy. Now, this concept, electronegativity, was developed so that we have some way of measuring the polarity of bonds. It was proposed first by Berzelius in 1811. Remember Berzelius? He came up with this way of representing elements. That's a long time ago. He studied that one. He did a bunch of other stuff too. And this concept of electronegativity was studied by other chemists because they thought, you know, it had merit in trying to understand how things were bonded together. And it was an attempt to quantitatively describe atoms in terms of how they would bond together. Would they bond ionically or would they bond covalently? And if we look at their electronegativities and compare the numbers that we get for them, we can see the difference between those numbers will tell us whether they have a very high ionic character to their bonds or a more covalent. And I'll show you that in just a second. There are various systems that were developed to express electronegativity. And in general, they all answer this question or subscribe to this statement. Electronegativity is the ability of an atom in a molecule to attract shared electrons to itself. So the scale that's most commonly used was devised by Linus Pauling in the 30s. Pauling is that scientist I told you about that had a way of synthesizing what we knew about chemical bonding at the time and putting it together into a coherent description. He wrote a complete book on the topic and was awarded the Nobel Prize for the nature of the chemical bond. In fact, that's the name of the book. Oh, he also got 2 Nobel Prizes. There are very few people who get a Nobel Prize in one area and get another one in another area. He got a Peace Prize in '62. I think he was anti-nuclear proliferation, which was kind of popular then in the '60s. Okay, so this is a simplified version of Pauling's method for determining electronegativity. I wouldn't try to reconstruct his table using this formula because I think it's more complex than that, but this helps us understand the reasoning behind. What we want to know is, first of all, what's the energy benefit from a hydrogen-hydrogen bond? If we're looking at trying to determine the electronegativity of one, what's the energy advantage of this bond? What's the energy advantage of this bond? And add those two together. and then divide by 2. And that will give us the expected bond energy for this species right here. And in this way, once you know, if we're going to compare this X to this hydrogen, if we know what the electronegativity of hydrogen is already, then we can solve for X as an unknown and put it in our table. And then once we know that one, we could even compare this one to something else. So it sort of cascades and snowballs. Once you've determined, or whether you determine it or not, or whether you just say, we're going to set this arbitrarily at a certain value, like we did with carbon, right? Carbon has 12 atomic mass units by convention. Well, maybe that's what we did with hydrogen. We just said, all right, it's going to be this value. Everything else is measured against that. And as we gather values for the other elements, then we can start, it'll start ballooning and we can get more elements in the system. The point here is that this value of electronegativity is relative. In other words, it's not an absolute determination. It's just saying if H has this value of electronegativity and X has this value of electronegativity, we can compare those two values and draw some conclusions as to whether we think the bond is going to be ionic or covalent, or it's going to be nonpolar or polar. So this is relative. These are relative values. Okay. So to do that, what we need is the difference between the actual and the expected bond energies. And this is an indicator of bond polarity. If hydrogen and our X have identical electronegativities, then the difference is going to be 0. Okay. If X has a greater electronegativity than hydrogen, then the shared electrons will tend to be closer to the X. So the higher the value of electronegativity, the stronger the attraction of that atom to electrons in a chemical bond. That's what we're saying. So if this one has a higher electronegativity than hydrogen, then we would say the electrons tend to move that direction. Even though we didn't break the bond, they just tend to spend more time here. And that would give us a slight negative there and a slight positive there. On the periodic table, and I think we've got an example here in a minute, the electronegativities generally increase from lower left to upper right, like our ionization energy. And we can think of them as second cousins. We know why, we have proposed why ionization energies increase from left to right in a period because of increased nuclear charge. There are more protons and they're pulling harder on the electrons. Okay? Or as we go down, the ionization energy decreases because we're adding ions to higher levels, and the inner levels are shielding that positive charge from the outer ones. So lower left to upper right is ionization energy, same for electronegativities and for similar reasons. In the Pauling scale, the highest electronegativity is fluorine in the upper right-hand corner. And we don't include the noble gases because they generally don't form compounds anyway. So if they don't form a bond, then we don't have to bother with them. And then the lowest value is 0.7 for cesium or francium. They both are the same. All right, so here's a periodic table that sort of gives you a three-dimensional idea of the electronegativities in the Pauling scale. Hydrogen is sitting up there by itself at 2.1. So if we compared hydrogen to fluorine, the difference would be what? 1.9? The difference in electronegativity would be 1.9 for hydrogen and fluorine. Okay. Or if we used sodium and fluorine, sodium and chloride, let's do that one. Sodium would be 0.9 and chlorine would be 3 minus 0.9. So that difference is 2.1, right? A little bit higher here. So this bond between chlorine and sodium is slightly more polar than the bond between hydrogen and fluorine. And that's how we assess the bond polarities. In fact, this value is so high, we consider that ionic. And I should have, let me see, do I have a table? I put the table in here. Yeah, there it is. It's coming up. Next slide. So let's look at lithium and fluorine react. Which has more attraction for an electron? Well, fluorine is way over there. Lithium's way over here. So fluorine should have the stronger attraction. It's the higher electronegativity. If we do fluorine and iodine, fluorine is still the more attractive because it's above iodine. All right. Lower left, upper right. Explain the trends. Well, across the period, it's the same as ionization energy. You have increased nuclear charge. And that means that there's a stronger attraction for electrons, whether it's the individual atoms or whether it's the atom in a bond. And down a group has to do with size and shielding. All right. So you may get different values for assessing the polarity of bonds or whether they're ionic or covalent. This is one way of looking at it. Other authors might give you a different value. From if the difference in electronegativities is 0 to 0.2, that's definitely covalent and it's nonpolar. Okay. If the difference is up to 0.3 to 1.4, then you have a polar covalent bond. If the bond is covalent, it's polar. Now, if the bond is between a metal and a nonmetal, there's potential for ionic bonding. And at that point, you're going to have values that may overlap a little. They might be in the 1 to 1.4 range. And if they are, if it's a metal and a nonmetal, then we would say it's not just polar covalent, it's ionic, perhaps with covalent character. And then anything over 1.5 is definitely ionic. So our HF and our sodium chloride were definitely ionic. Okay, so let's look at these. Following bonds, let's order these from most to least polar. A has a group of fluorides. So this one should be fairly easy to tell the difference. If we want most to least polar, and of course, we have to assume that these are covalent to call them polar. So we just need how close are they to fluorine? So who's closest to fluorine to be the least? Well, most to least. Let's do the most. Which one's the farthest from fluorine on the periodic table? Carbon. Yeah, carbon's farthest to the left, so it would be the most polar. And then the next would be nitrogen, followed by oxygen. So that should be the order of polarity, just qualitatively. Carbon, nitrogen, oxygen, okay? B, let's see. There's a fly in the ointment here. We've got carbon, fluorine, nitrogen, oxygen, and silicon fluorine. So we have to look at our periodic table and look at the proximity of one to the other. Carbon to fluorine they're pretty far apart. But silicon to fluorine is even further apart. Right, so silicon fluorine should be greater than carbon fluorine, and nitrogen oxygen are right next to each other. So they should be the least polar. In fact, silicon and fluorine might even consider that ionic. I'd have to look at the exact numbers to tell. Let's go back and see. No. Here. Silicon is 1.8 and fluorine is 4. So that's what? 3.2? 2.2. Yeah. That's ionic. So technically, calling that polar is kind of a misnomer, because that's an ionic bond there. Anyway, let's look at C. Oops. Give you the answers. So for C, we're trying to look at chlorine, chlorine. That's going to be completely nonpolar. So we know it's going to be over here. And boron and chlorine and sulfur and chlorine. Okay. So how far apart? Boron and chlorine are pretty far apart. Sulfur and chlorine are right next to each other. So sulfur and chlorine should be here, and then boron and chlorine should be there. So boron, sulfur, and the dichlorine. Okay. Let's see. Somebody else show up while I was talking. No, we're good. Everybody's here. All right. Now we are going to take those values into account. So if it was, if we're differences in electronegativity, and whether it's non-polar, polar, or ionic. Ionic needed to be what? Greater than 1.5, I think. Greater than 1.5 difference. And this is 0.4 to, was it 0.5? I can't remember. There it is, 0.2. So this is 0 to 0.2, and this is 0.3 to 1.4. It's polar. Okay, now we can answer the question. Which of the following bonds would be the least polar, yet still be considered polar covalent? Okay. If it's going to be covalent, we can't have a metal and a non-metal. Magnesium and oxygen are definitely going to be too far apart. 1.2 and 3.5. Let me put these up here so we can deal with them one at a time. Carbon, oxygen, oxygen, silicon, oxygen, and nitrogen, oxygen. Okay. So let's just put the values up here. 1.2, and oxygen is 3.5. 3.5. Nitrogen, 3.0. Silicon, 1.8. And carbon, 2.5. Okay. So this difference is going to be 2.3, right? This one's going to be 1.0. This will be 0. This will be 1.7. This would be 0.5. Okay. All right, which are going to be ionic? Well, definitely this one. That's a metal and a non-metal. So that's not going to be covalent. We can't say it's polar because it's ionic. This one is also too large. Okay. And this one is covalent, but it's definitely non-polar. So it's a toss-up between these two. Carbon and oxygen. No, it's saying nitrogen and oxygen. Oh, did I read those wrong? No, that's right. What's the question? Least polar. Sorry. I was looking the wrong. I was doing most. Least polar. And still covalent. So that's 0.5. Difference between 0.5 and 1. That's least polar. So when you have the values, it's fairly easy to determine which is which. This one is most polar without being considered ionic. Okay, in that case, this is least, and this is most. Should be there. Okay. All right, there's a term for these covalent bonds that expresses their polarity. And it's derived from physics. And it's called the moment. The moment is a term used in physics for directed force. So if I have a, so I'm trying to move a box, slide it on the floor, and I'm standing up here and the box is down there and I'm pulling this way, all of that force is not going this direction. Right? Only a component of this force is going that direction. And we can determine what that moment is. There are two moments involved. One, the angle of this force says I'm trying to lift it and I'm trying to move it that way. And those can be separated as vectors. In our context, for dipoles, this dipole moment is an expression of that property of the molecule where you have a charge, unequal charge distribution. And it can be represented by a positive charge on one side and a negative charge on the other. So if we have, and I drew this earlier, if we have two atoms in this bond and say the Y is the more electronegative, and we do have a polar bond, then we can say, there's your moment. This says that's the positive side, and this is the negative side. That's the way we express it. Okay. Now that's just for the bond. We're really interested in the whole molecule. If we've got a covalently bound molecule like water, we know from experience and you'll be able to do this yourself too later, that the oxygen the water molecule is bent. It has these hydrogens over here and here, and it has unbound lone pair electrons there. The bonds are polar this direction toward oxygen. Okay. But when we want to consider the overall possibility for polarity of the molecule, we have to consider two things. One, we have to consider, are the bonds polar? Are the bonds in the molecule polar? In this case, yes, polar bonds. Then we have to consider the geometry of the molecule. Because if this molecule were linear and the hydrogens were out here and here, they would be a moment, a dipole moment that way and one this way, opposite in direction and equal in magnitude, would cancel each other out. And that would give you overall a nonpolar molecule. But they're not. They're bent and they're facing generally that direction. So if we do what we call in physics a vector summation, you get a value that's like this overall for the molecule. This is the negative side of the molecule. This is the positive side of the molecule. So those two factors have to be considered when we're looking at if we want to determine the dipole moment of a molecule, individual bond polarities and geometry. If the bond is nonpolar, right? If you have, say, two nitrogens, right? You don't need to know the geometry of the molecule because there are only two atoms, and that's a nonpolar bond, so the whole molecule is nonpolar. Or if we have carbon dioxide, like that, then we know that this bond is polar that direction and this one's polar that direction. And I didn't draw them to scale, but they're opposite and equal in magnitude. The bonds are polar, but they cancel each other out because of the shape of the molecule. Okay, we're going to be able to do that eventually. There's our water molecule with its dipole moment. And just take my word for it. We don't have time to go into the physics of vector summations. Or take a physics class. How about that? There's our carbon dioxide. And that's not drawn correctly because it shows a single bond. There's double bonds between the carbon and the oxygen. There are typical shapes that we're going to look at eventually. You have the linear, of course. Carbon dioxide is a linear molecule. In other words, if this is the fulcrum and we're looking at the angle of the bond, right? If it's just that, then there's really no angle to deal with. But if you have three atoms, the angle of this bond is 180 degrees. That means it's linear. If you have four atoms, and our example here puts, I think, A here. Excuse me. Let's do this. Puts A in the middle, and it's bonded to three B's. And they tend to separate, they try to be as far apart from each other as possible. This gives us an equilateral triangle, right? We call this trigonal planar. Now the bond angles here, this is the overall, the outline of the molecule. These dots don't represent any kind of bonding. It's just to describe the shape of the molecule. The bond angle in this case would be, right, all the way around would be 360, right? So divide that evenly, and that means the bond angle is 120 degrees. Okay. If we have five with one in the middle, so if we have an A in the middle, we have a B up here, we have a B down here, and a B in the back. and we have that trigonal base, and then we have that, what we're looking at is a tetrahedron. You have to sort of visualize it. Well, we've got a model there set up. Carbon tetrachloride is a good example of that one. The bond angle here, right, between say A and B, and this A and this B is 109.5 degrees. That's really the only one that you have to memorize. The rest of them can be deduced. All right, we'll get back to those in just a minute. When we talked about electronic configurations and the valence electrons, remember those? Okay. What atoms are trying to do when they bond, this is another explanation for bonding. What atoms are trying to do is to obtain or attain the noble gas configuration in their electronic structure. So if you have noble gas configuration can be summarized for period 2 and period 3 fairly reliably as an octet. It's trying for the octet. In period 2, you're trying for a 2s and a 2p complete. So the 2 electrons there and 6 here. That's an octet. For the third period, it seems to work out fairly well too, an octet. When you get down into the fourth period, now you're introducing Ds, and that messes everything up. But for period 2 and period 3, the octet is a good rule. There we go. Like I said, periods 4 and above tend to get messy. Actually, what they give you is multiple possible routes to stability. Let's just put it that way. For 10, which is in, here it is in the 5th period. 10 tends to either be a 2+ or a 4+ charge as an ion. And that's because, let's see, 10, let's just draw 10. So 10 has 50. But it has a krypton core at 36. Then beyond that, it has a 5s2 and a 4d 10 and then a 5p2. That should be 36, 46, yeah, 50. So these are the valence electrons. If we lose 2 of the highest energy ones, we get a +2 charge. Okay. If we lose those 2 plus the next 2, we get a +4 charge. So that's why 10 prefers either a 2+ or a 4+ charge when it forms ions. And we can use the same reasoning for lead. Lead is in the 6th series, but it has a similar, it would be 6s and 6p instead. But for the same reasons, it wants a 2 and a 4. Bismuth, on the other hand, is right next to lead. And it actually has, bismuth would have this, and this, and that. Oops, sorry. E. There we go. And in that case, losing those three, we give it a 3+ charge. Losing those three, these two, we give it a +5 charge. So bismuth prefers 3+ and 5+ ions. And thallium, let's see, where's thallium? Right here. 1 electron in its P, 2 in its S. So it could either lose one and be a +1 charge, or it could lose all three of them and make it a +3 charge. All right. Stable compounds. Let's make some room here. Videos don't show how hard I have to rub that thing to get it clean. Looks easy on the videos. So when two metals react to form a covalent bond, they share electrons in a way that completes the valence electron configuration of both atoms. And we'll look at examples in just a minute. When a nonmetal and a metal react to form a binary ionic compound, then we get transfer of electrons from one to the other. So for sodium and chlorine, so that's a complete transfer of electrons. And that's because the electronegativity of chlorine is so much higher than it is for sodium. It has enough pull to strip that electron away from it. And sodium is happy to give it up because it would complete its outer shell. We can also look at these. It's deja vu. It feels like we've talked about this before. Isoelectronic series. Did we talk about those when we were doing electronic configurations? We didn't? Have we done electronic configurations? We didn't? Oh, I'm sorry. Nobody said anything. Wait. Yeah. Yeah, we had to, because of the way we talked about the periodic table, filling orbitals, s orbitals, p orbitals, d orbitals, f orbitals. Yeah, we have done it. An isoelectronic series is simply a group of atoms and ions that have the same electronic configuration. And they get that electronic configuration. Most of them will be ions, because if they're all neutral, then they have different electronic configurations because they have different numbers of electrons and the same number of protons. So they're all going to be different. You can't have two neutrals be the same electronic configuration. But if you make ions, and a good example, not the only way to do it, but a good example is to start with a noble gas and either add electrons or subtract electrons. Would have the same configuration as krypton. And strontium, 2+, would have the same configuration. So these would all be isoelectronic because we have completed their valence shells. We made them look like a noble gas. The This wants us to choose an alkali metal, alkaline earth, noble gas, and halogen so that they can constitute an isoelectronic series. Well, we already did that right here. All right, this is another way, starting with argon. You could do a similar thing. Argon, add 1 electron to chlorine and you get argon. Right? Or if you go down to potassium and lose an electron, you get argon. Calcium, you lose 2 electrons, you get argon. And the electronic configuration of each one of them will be exactly the same. They will look like argon. The number of electrons will have to be exactly the same also, because they have the same electronic configuration. But the number of protons is still characteristic of each of the elements. So potassium still has 19, calcium has 20, argon has 18, chlorine has 17. Protons. Remember, that's the Z number. That's the atomic number and characteristic of each element. If you change that value, you change the element. But you can have the same number of electrons. What we're trying to get at here is working toward a concept that will justify forming a chemical bond. All right. What we've done so far is ionization energy, trends in the periodic table. Ionization energy, radius, atomic size, and electronegativity. We haven't done ionic radius. Ionic radius is a little trickier because if you add an electron to get an ion, you are causing the size of the ion to balloon, to get bigger. If you subtract an electron, then you're making the ion smaller. That's why in our representation of sodium and chloride, sodium was the tiny positive cation, and chlorine was the big anion. Okay, so what are the factors that influence the stability and the structure of solid binary ionic compounds? Well, since ionic compounds are electrostatically attracted to one another, we can learn something, or we can quantify the strength of the bond with this term called lattice energy. Lattice energy has a specific definition. And I thought it was going to, yeah. Well, let's do that first. Lattice energy. We'll use something simple, like table salt. Lattice energy is the energy that's released because we're going from a high energy to a low energy to get the bond formed. So lattice energy for an ionic compound is we start with the gaseous ion, the cation, and the gaseous anion. And they come together and form the solid. That's the expression for a lattice energy. When they do that, they give up energy. Okay? Sometimes a lot to form an ionic compound. Now we can calculate this using modified Coulomb's law. The K might be a little bit different though, but the relationship between the positive and the negative charge and the distance between them is still the same, still relevant. But we know that when we bring these elements together in their common state, sodium would be a solid, right? And chlorine would be a diatomic gas. So to get from here to there, we have to do a couple of things, right? We have to heat this up and make a gas out of it. That's going to take energy input. Okay, so that'd be a positive value. That's endothermic. Then we have to take this gas and we have to add energy to that. That's endothermic. And make the sodium gas ion. So what does that look like? Remember that one? Ionization energy. Right? So this is ionization energy. For chlorine, we have to add enough energy, another endothermic process. We have to get those atoms apart. So there are two of them. Then we can make an ion out of them. Right, so we have this gas, we add an electron, and that makes this one. So what does that look like? Electron affinity. And in this case, this is exothermic. Okay. So once we get to this point where we have this ion and this ion, then we can go to this step and form the ionic solid. So that's what these next couple of slides are saying. Sublimation of the solid metal. So this is sublimation. I'll let that term out. Which is endothermic. And then we take it and we use ionization energy, right, to get it to there. And then it's ready. Now we go to the non-metal, right, and we break it apart. So in order to end up with just one of these, we have to change our coefficients. So if we want one of those, then we're only going to have half of that one. And then the next page is the electron affinity. Like that. And then we can put them together here. And this is the lattice energy. Now that term comes from the fact that ionic compounds tend to form a regular arrangement of cations and anions in a crystal lattice. And we're going to look at that in more detail second semester. But that's where the term comes from, lattice energy. And it is very, very exothermic. Negative, 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 negative. Lots of energy comes back from that. Now, since these energies, since delta H is a state function, we can break it apart into these separate steps and add these together and get the overall for the formation of the compound, for the reaction. If we take the reaction, we're simply saying sodium solid, or did I do that already? No, I didn't. Sodium solid plus chlorine gas yields sodium chloride solid, and that's 1/2 of this one. And this is the overall reaction, and these are the individual steps. And if we know the energies for each one of these, then we can calculate that one because they're all state functions. Right? Doesn't matter how they got there. And that's what this graph is trying to show. Okay. So here's a real example for the reaction of lithium plus fluorine gas to yield lithium fluoride solid. That's an ionic solid. We sublimate the solid lithium by adding 161 kilojoules per mole. And then we take the lithium and strip an electron from it, ionization energy. That's 520 kilojoules per mole. Okay. Then we take the fluorine and we break that apart. So we actually need half of its bond energy. Break the bond. All right. I didn't name anything. This is bond energy. Bond energy. Chlorine with chlorine. But we only need half of it. So we have to take that value and cut it in half. That's endothermic. And then we take that individual fluorine and add an electron to it. That's electron affinity. And that gives up energy. And then we can take the individual ions and form the solid. That's the lattice energy. So we had 1, 2, 3, 4, 5 steps to describe that one reaction. And then we add those values together and we get an overall change of minus 617 kilojoules. So this is an exothermic process, a very exothermic process. Minus 617 kilojoules for that reaction. All right. This is just summing up the individuals. This is like Hess's law. In fact, it's exactly like Hess's law. All right. So I mentioned earlier that there are no bonds that are perfectly 100% ionic, even with compounds that have a maximum possible electronegativity difference, such as fluorine with cesium. That would be the biggest difference you can find in the periodic table. We can't reach 100% ionic character because we don't know what the ceiling is, right? There are no elements that are greater than that in electronegativity in fluorine and less than that for cesium. Unlike if you're bonding to exact alike elements like 2 hydrogens, 2 oxygens, 2 nitrogens, they have exactly the same electronegativities. Their difference is 0. So we can calculate that and say those are perfectly covalent, 100% covalent. But we can't do that for the ionic. We can determine the ionic character of a bond if all we have to do is be able to measure the dipole moment of the bond itself. Measure the dipole moment of an XY covalent bond, and then calculate the dipole moment of the XY ionic bond and ratio those two. That's what that formula is telling you to do, times 100, and that will give you the percent ionic character. If we do that for various binary compounds, then we can put them on this chart of where the percent ionic character is on the y-axis and the electronegativity difference between the two elements is on the x-axis. And we see that there's roughly a straight line from lower left to upper right with a positive slope. So we know that the reds are considered ionics, and HF is kind of in the gray zone, as is lithium iodide. But the ones with the least percent ionic character are where you get very close together in the periodic table and electronegativities, the blue ones. All right. There's I don't know if I ever told you this story. When I was working on my PhD, I was working, it was with soils. And I was particularly interested in fractions of manganese that were contained in the soil. You know, where is this manganese living? Is it in this crystal? Is it in this organic phase? Where is it? So I had a series of extractants that I was using to remove manganese selectively with stronger and stronger extractants. And I would determine the concentration relative to the soil. And I asked one of my advisors, who was our soil chemist, I said, how do I justify these things theoretically? You know, what am I saying here? And he basically told me, your extraction technique is operationally defined. In other words, it's whatever you say it is. That's what we've got here with the definition of an ionic compound. It's operationally defined, right? We just try to get close to reality, but in the end, it's just whatever we say it is. Any compound that, and in that respect, if we're saying a compound is ionic, then as long as it's, we can separate it into its component ions. One way to do that is to heat it up and break that ionic bond. We get separate ions. If we can do that, then we can pass an electric current through it because we have mobile ions. Right? If it's a solid, those ions are stuck. They can't move. So a brick of sodium chloride, I'd like to have one, but like that size, perfect cube. You put electrodes on either side and you get no current through it because the ions cannot move. But if you melt it, then the ions can move. Or in the case of some ionic compounds that are soluble in water, then all you got to put them in solution and they will conduct electricity. Well, that's the definition. An ionic compound is one that will conduct electricity when melted or dissolved. Okay. That's an operational definition of an ionic compound. Remember what the difference between a law and a theory. A law just says, this is what happens. Give me these circumstances, these values measured for the variables. I'll plug them in my law and it spits out an answer. That's it. That's as far as you can go with it. Or it could be a descriptive law in terms of, say, Newton's first law of motion. Right? An object at rest tends to stay at rest unless acted upon by an external force, and an object in motion tends to stay in motion unless acted upon by an external force. Right? It's not quantitative, it's just qualitative. And then his second law is force equals mass times acceleration. That's a quantitative law. But we can't modify it. It just is. It says this is what happens. For a theory, we're saying this is why something happens. In other words, if we say it happens for this reason, what if we change that reason? We tweak it some. You know, what's it going to do to the theory? So the theories in effect are more powerful because they are modifiable and they are predictive if they're accurate. And very often a theory will be accompanied by a model. Sometimes it's a physical representation of reality, right? Models are not reality. They are macroscopic representations of the microscopic world, as far as chemistry goes. And a model can be modified. Right? If you make a model airplane and you change something about it, say your model airplane is designed to fly. Right? You've got a model airplane, it's got an engine in it, and it's flying. What if we change something? Maybe we make the wings bigger. You know, what does that do to its flight characteristics? So we can change the model, and how does it affect the theory? It has different outcome. So these are the precepts behind the use of a model. A model does not equal reality. That's the first rule. Models are oversimplifications of reality. And for that reason, very often they're wrong. Now, they may be right in certain limited circumstances, but if we push them too far, they turn into wrong. Right? And I mentioned earlier, I think, what do you do when your theory fails or when your model doesn't work anymore? Right? We can limit its application. Right? Once we find out the boundaries of where a model doesn't work anymore, then we can limit its application. And that's what we do with classical physics, Newtonian physics. Right? It doesn't work at the small levels, doesn't work at the big levels. Or we can modify it. And many models are affected that way. We modify them so that they will accommodate a greater range of variables. Or we can discard them, start over. Okay. And then I added one more. This is mine. I didn't read this one. Turn it into a religion. Yeah. And that's what we've done with global climate change and the most famous ones that have been turned into a religion, global climate change and Darwinism. They are religions. They're not sciences anymore. Okay. So what else are we have to be privy to? Models become more complicated and are modified as they age. That would be this option here. Number 4, we must understand the underlying assumptions in a model so that we don't misuse it. Okay. That very often is ignored by some scientists, especially if they move into the 4th category. Right. Then they completely ignore underlying assumptions. And not only that, they ignore the data. The data that says your model's wrong, they just sort of pick and choose the data so it'll fit the model. And number 5, when a model is wrong, we often learn much more than when it's right. That's true. Models are not wasted if they're proven to be wrong. They're like, let's see, who was it? Oh, my mind's gone blank again. Edison. When Edison was asked, you know, how'd you feel when you didn't invent the light bulb, when you got it wrong all those many times? He says, I didn't get it wrong. I just learned that you can't make a light bulb 99 different ways. There's only one way that I can make a light bulb, and I discovered that. So once you find out the wrong way, you know that don't go down that path. All right, and this is, oh, I should have waited. The slide's ready for you. Restrict the model's application. Okay, Newton's laws. Newtonian physics only work in a narrow range. And if you get too big, like black holes, it falls apart. Or if you get too small, like electrons and protons and atom size, then it falls apart. So on the small size, we use quantum mechanics, and on the big size, we use relativity. And they haven't been reconciled completely yet. I'm sure there are people working on it, trying the unified model of the universe. All right. You can modify it to accommodate the new conditions, right? It can get pretty ridiculous too. There are some physicists that propose 26 dimensions of the universe, right? We only know of 4 that we're using in this course, right? Height, width, breadth, and time. And the other 22 dimensions are mathematical. Throw the metal out and start over again. That's what they did with J.J. Thomson's plum pudding model of the atom, where you have the electrons in this mix of positive matrix. And Rutherford proved that one wrong, and it died instantly. Oops. Oh, okay. I left out the religion. Bond energies. All right. So we know we got bonds. We need to define what we mean by a bond energy. To break a bond, energy must be added to the system. It's an endothermic process, and the value will be positive. So bond energies are expressed in terms of forcing them apart, breaking the bond. When the bond is formed, then the energy, that same amount of energy is released. So once we get that number, we can talk of it in terms of breaking it or forming it. The value of the number is the same, we just change the sign. Most bonds are one of 3 types: single bond, double bond, triple bond. Now, this is our starting point. It can get interesting. And like I've said before, nature just does what it does. And we're trying to figure out how to explain it, try to rationalize what's happening at the microscopic level. And this is our starting point: single bond, double bond, triple bond. A single bond is represented by a line between 2 atoms. And that represents a pair of electrons. A double bond we represent with 2 lines, and that's 2 pairs of electrons. And obviously, 3 pairs of electrons is a triple bond. I've never seen a quadruple bond. Maybe they exist, but I haven't seen. One thing we know is that the bond length decreases with the more bonds you have. So this will be a shorter bond than this one, and this will be a shorter bond than that one. It's not a linear progression. In other words, you don't go from here to here. This one isn't half the distance of that one. It's more like 75 or 80%. It's closer, and this one's closer also. It's not linear progression. Also, maybe that's on the next slide. Oh, I didn't put it there. Not just the bond length, but the bond strength increases. In other words, it takes more energy to break this one than it does to break that one. And it takes more energy to break this one than it does that one. So the strength of the bond increases and the bond length decreases as you increase the number of bonds. These values have been compiled to represent values for the bond energy. In other words, they're all positive values. So they're represented in terms of how much energy does it take to break that bond. So a hydrogen-hydrogen bond will be broken by 432 kilojoules per mole of those bonds. Now, why do we want to bother with all those? Because if you know bond energies, you can calculate the enthalpy of a reaction. You know all the bonds that are broken and all the bonds that are formed, then you can calculate and get pretty close to the actual energy that's involved in the reaction, whether it's exothermic or endothermic. All right. And there's the formula. So this delta H, or the enthalpy of the reaction, you take the energy required to break the bonds, right? So those would be all positive values. And you add up those energies times the number of bonds that are in the reactants. The energy required to break the bonds will be on the reactant side. Then you take the energy that's released when the bonds are formed on the product side and subtract those. And the reason we subtract them is because we need the bond energies are given as positive values. And if the bonds are formed, then that's an exothermic process, and that's a negative number. So we need to put them in the negative position. Okay, that's the way the formula is constructed so that we can use all those positive values in a formula and get the right answer. That this value is a Greek letter. I don't know if you've seen it before. Sigma. It just means summation. Okay. So let's see. We got an example. So in this case, we've got CH3N with a C triple bond. It's written like that so that we know what bonds we're dealing with. These are single bonds at CH3, and then there's a single bond to the nitrogen and then a triple bond to the carbon. And then afterwards, we're still going to have this one, but now this one's going to be bound to the carbon with a triple bond to the nitrogen. And they're both gases. Now, if we follow the formula completely, then we'll say carbon hydrogen, 3 times the carbon hydrogen bond, 3 times 413. Okay. And then 1 nitrogen bond, which would be 305. And then 1 nitrogen carbon triple bond, which would be 891. And then we would subtract what's on this side. But look, it's the same. It's the same on both sides. This one right here goes right there. And then we would add second, nitrogen carbon. Oh, I left out one, didn't I? I left out carbon nitrogen plus 1 times carbon nitrogen single bond, 305. There we go. So this one's the same for here. And the carbon-carbon bond would be 1 times 347. And these are all in kilojoules per mole. And then we have this one, 1 times 891 for that one. So notice that this is the same on both sides. So this one subtracted from that one is 0. Right? And this one, subtract that one, is also 0. So really all we have is 305 minus 347. Minus 42 kilojoules should be the answer. Okay. Now, if there were all different bonds in there, then you would do the whole calculation. But in this case, we've kept that one and that one the same on both sides, and this is the only one that changed right in here. That's what made it easier. Okay, normally what I would do is pause and we'd come back later. But we're not having a lab today. But you can't have a break if you need one. You need a break? No? Okay. We'll keep going then. I guess we'll keep going. We'll get finished sooner. And since I didn't bring donuts or pizza, we can't stop and have lunch. Oh, some instructors do that. Okay. So now we're going to get, now that we've got an idea of what the bond is and how to deal with it, we're going to look at theories that help us understand not just the nature of the bond, but the structure of the molecules. And the earliest theory that actually produced usable results was the valence bond theory. And the valence bond theory simply says that when bonds are formed between two atoms, they are formed by the overlap of two atomic orbitals. The outermost valence orbitals overlap to form those bonds. Okay, and we're particularly talking about covalence here. Right, ionic bonds are pretty simple. They're just Coulombic attractions between opposite charges. So now we're getting into covalent bonds only. The model that accompanies this theory is called the localized electron model. And it follows from the theory because it says that in the bonding process, those electrons still belong to the atoms they came from. Right? They just share their electrons by overlapping their orbitals. Now, this is derived from the new developing theory called the quantum mechanical model. And we got into some quantum mechanics with Schrodinger's equations for electronic structure of atoms. We had the four quantum numbers: the principal number, the angular momentum, the magnetic, and the spin. Those four numbers go into Schrodinger's equations for individual atoms. Localized electron model extends that model, tries to extend the model to use it in covalent bonding. And we overlap some of those valence electrons orbitals. And there are some names at the bottom. These were prominent developers of that theory. Linus Pauling was one of them. Okay. So for the localized electron model, we have number one, we have electron pairs are assumed to be localized on a particular atom or in the space between two atoms. In other words, if we have a bond expressed here between two atoms, then the electrons here are known as, these are bonding pairs. Those are bonding pairs. And if they have any other pair of electrons somewhere else, these are lone pairs. Or you might also see non-bonding pairs. Okay, two types. The lone pairs are localized to a particular atom. The bonding pairs are shared in the space between atoms. Okay. Now, what we're going to do is we're going to go part one and part two here, item 2 and item 3. We're going to finish those today and then save part 3 for chapter 9. Okay. So we're gonna get into the rest of this model plus another model that's associated with it called the VSEPR. I'll describe that in just a second. But first, we need to know, you've seen me do things like this. And these, that 2, 4, 6 electrons there and 2 here. So that nitrogen thinks it has an octet, right? 2, 4, 6, 8. And this one thinks it has an octet, 2, 4, 6, 8. But how did I get there? This was a method developed by G.N. Lewis, who was an American chemist in the early 20th century, to help him understand what was going on between atoms in the bonding process and how to best express them in terms that would limit the number of electrons that could be positioned around an atom. In the beginning, it would limit the number to an octet. So his model, Lewis's dot structure model that he was using works best for first, second, and third periods, where we have that bona fide octet. And it also assumes that when you write a symbol for an atom, it may start out with, I don't know, 3 electrons in its valence shell, and we only represent valence shell in this model. But if it bonds with something else, maybe it's picking up the other electrons that it needs to complete that shell in the bonding process. Okay? So we need to learn how to use the Lewis's dot structure. If you're dealing with hydrogen, we have a duet rule because hydrogen only has the 1s orbital. And it's complete when it has 2 electrons. That's the duet rule. For the rest of them, in the second and third period, we have the octet rule. So what they're trying to do is, with an octet rule, is to acquire 8 electrons. Okay. Single covalent bond for hydrogen is obviously, it gives each hydrogen the feeling, if I may anthropomorphize, hydrogen has the feeling of a duet. So if you look back, okay, it thinks it has 2 electrons, thinks it has 2 electrons. We didn't create electrons. It's just the appearance of 2 electrons for that hydrogen and 2 for that one. We know that there's only 2 electrons total, but by bonding and sharing, they have the appearance of a complete 1s shell. Whereas with carbon and oxygen, how many electrons does carbon have in its valence electron, in its valence shell? Well, count over from the left. Lithium, beryllium, boron, carbon. It has 4 electrons in its valence shell. And we would write those like this. Okay. How about oxygen? Well, oxygen is 2 more over, so it would have 6 electrons in its. Like that. Or like this. Okay. That's before the bonding occurs. So what happens is, in order to keep everybody happy, right, with their octets, this oxygen would share that electron with this electron and make a bond. And this electron with that electron and make a bond. So now oxygen here thinks it has 2, 4, 6, 8. And on this side, we would do a similar thing. Now this oxygen has 2, 4, 6, 8, but the carbon also thinks 2, 4, 6, 8. So by forming a double bond with that oxygen and a double bond with this oxygen, and this oxygen still has lone pairs, but that carbon doesn't have any lone pairs. We have constructed an octet for each of the members of this compound simply by sharing. All right. Nitrogen, let's do nitrogen. Okay. Nitrogen has how many valence? Lithium, beryllium, boron, carbon, nitrogen. 5 electrons in its outermost. Right, 1, 2, 3, 4, 5. Like that. So in order to complete its octet and have only 2 nitrogens involved, we would share like that, share like this, share like that. Makes a triple bond. And that's 2, 4, 6, 8, 2, 4, 6, 8. We make the octet for nitrogen. All right, now how do we do Lewis structures? We did Lewis structures before, didn't we? For individual atoms. We didn't do those? Okay. The Lewis structure for an individual atom is simply the valence electrons, right? Once you know the valence electrons, and we can find those easily from the periodic table. But to do it for a whole molecule, these are the rules. You sum the valence electrons from all the atoms in the molecule. Now, how do we know what the molecule is like? You're given the molecule. Carbon dioxide, methane, whatever, sucrose or glucose. You're given the molecule, and then you work out the structure from that. You know it exists because it's been isolated and characterized. So you don't have to do that. And then you add up all the electrons that are bound to the atoms. Then you take the atoms and you hook them together with single bonds and subtract 2 electrons for each bond from the total. Then with the leftover electrons, you start from the outside and work your way in. You make octets for each one of them as you work your way in. All right. So let's, unless for hydrogen, then it's a duet. Water's too easy. Let's do one that's a little more difficult. Let's see. How about PBr3? You could do that one. Phosphorus tribromide. Okay, phosphorus is 5 over from the left. It has 5 valence electrons. Bromines and halogens, so each one of the halogens has 7. That's 7 times 3. So it's 21 plus 5 is 26. Total electrons. Then here comes the tricky part. We try to decide, and in the beginning, we're going to start with simple molecules. We try to decide which one's in the center. Okay. We generally assume that the first one is in the center, but maybe it's not. Like, especially if we're describing an acid, then it might be different. But one other rule is the one to the left, the one that's more metallic, is in the center. So phosphorus is to the left of bromine, it goes in the center. And then we form a single bond with each one of the bromines. 2, 4, 6. So we're going to subtract 6, that leaves 20 electrons that we have to position. So we're going to put 20 electrons, or as many as we can, to make an octet for bromines. All right, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've used up 18 because now we have 2, 4, 6, 8. Each bromine has an octet and we can't put any more. So we have 2 electrons left over. We're moving in. Those 2 electrons have to go on that phosphorus. Okay. And that gives the phosphorus an octet, 2, 4, 6, 8. So we've used them all up and we got lucky. They all have an octet now. That would be a valid Lewis dot structure. All right. There it goes right there. Now, how about hydrogen cyanide? That presents a little problem that we are going to solve. Hydrogen cyanide. So hydrogen has 1 valence electron, carbon has 4, nitrogen has 5. All right, so that's 10 electrons. So which one goes in the middle? Well, hydrogen doesn't count. Carbon's to the left of nitrogen, so carbon goes in the middle. And nitrogen here, hydrogen there. It's either nitrogen in the middle or carbon in the middle, and carbon is to the left of nitrogen, so we put it in the middle. Plus, that's the way it's written. So that's minus 4 electrons, 2, 4. We have 6 electrons. Hydrogen can't take any more. So we got 6 electrons, 2, 4, 6. Okay, they're all gone. But we don't have an octet around carbon. We got an octet around nitrogen, but carbon needs one. So how do we do that? Well, we can't do anything from this side without messing with that bond. So we have to do it all from this side. If we take these 2 electrons, make a bond out of them, and take these 2 electrons, make a bond out of those, 2, 4, 6, 8. And we still have 2, 4, 6, 8 around nitrogen. So nitrogen, carbon nitrogen is a triple bond. Carbon hydrogen is a single bond with 1 lone pair. That's a valid Lewis dot structure for hydrogen cyanide. Okay. These are real simple. They can get messy. But we got some rules that'll help us. Okay, hold on a second. Why does it keep doing that? All right. We haven't talked about discerning the structure. Water as a Lewis dot structure is HOH with 2 lone pairs over the oxygen. Lewis dot structure for hydrogen, well, those are too easy. How about ammonia, NH3? Okay, we know that's ammonia. So 5, 3 times 1 is 3 equals 8. 8 electrons. So we know that nitrogen has to be in the middle because hydrogen can only have 1 bond. Right? It can't accommodate any more. So we form a single bond with each of the hydrogens, like that, and that takes care of 6. So we have 2 electrons left over. They have to go on this nitrogen. And hydrogen has its duets, nitrogen has its octet. That would be a valid Lewis dot structure for ammonia. We've done carbon dioxide before. Carbon tetrachloride, you could do that one. Chlorine is 7 times 4. And carbon is 4 of it. Yeah, 4. So 8 times 4 is 32 electrons. Carbon goes in the middle. It's to the left of chlorine. 1, 2, 3, 4. Chlorine, chlorine, chlorine. Chlorine, 2, 4, 6, 8. Minus 8 here is 24 electrons. If we put 6 around each one, that would give them each an octet. And that would be 6 times 4, which would use up all their electrons. So that's the valid Lewis dot structure for carbon tetrachloride. Okay. Now, for some of the oddballs, boron trihydride. This is a real compound. We know it. Now we got to explain it. So boron has 3. And 1 times 3 is 3. So we have 6 electrons. Boron goes in the middle. Hydrogen's here, hydrogen here, hydrogen here. 2, 4, 6. Use them all up. All right. We cannot make an octet for boron. It's deficient. And we just have to accept it. It does not have a complete octet. And that's not unusual for compounds. Boron and beryllium do that a lot. Okay. Now we go the other direction where we have to exceed the octet. For instance, let's do arsenic pentabromide. Okay. Arsenic is down here, right? If we only count the 4s and 4p's, there's 1, 2, 3, 4, 5. So that's 5 valence for arsenic, 7 times 5 for bromine. So 8 times 5 is 40. 40 electrons. Arsenic goes in the middle, and we have 5 bromines. So that's 2, 4, 6, 8, 10. 30 electrons. If we put 6 more electrons around each bromine, we get an octet. And 6 times 5 is 30. So there we have all of our electrons used up, a valid Lewis dot structure, but arsenic exceeds the octet. In fact, it has 10 electrons around arsenic instead of 8. Now, how do we justify that? Well, the fact that arsenic has d orbitals. So the d orbitals are getting involved somehow. That's the only thing that makes sense. We have 4d orbitals. Okay. And we can say the same thing for sulfur, right? Sulfur so it can also exceed the octet. And in this case, it has. Now, as we try to do more and more with these Lewis dot structures, we find out that they have kinks in their armor. And they're not going to work well with everything. But it's a start. And it helps explain many of the observed physical and chemical properties of our compounds. Boron trifluoride, boron pentachloride, and sulfur hexafluoride. Okay. Now, in this case, boron does have an octet. Right? We could draw that. phosphorus pentachloride exceeds the octet, right? You can tell there, 2, 4, 6, 8, 10 for that phosphorus. And sulfur hexafluoride has 12 electrons. Okay. Carbon, nitrogen, oxygen, fluorine will always obey the octet rule. Boron and beryllium tend to go less than sometimes. Second row elements never exceed the octet rule. Third row elements sometimes do exceed the octet by using d orbitals. If you have any leftover electrons as you're proceeding, put those electrons on an atom that has access to d orbitals. All right, here's another problem. Right, remember our theories and models, they start to break down and we have to accommodate them. This nitrate ion, right? Our polyatomic ions are covalently bound for stability, but they do have a charge. So when you are introduced, when you're presented with a polyatomic ion and you're counting up the number of electrons to do the Lewis structure, you'll do the neutral atoms first. This is 5, and this is 6 times 3, and then plus 1 for the charge. So this is 5, 6, 24. Okay. Nitrogen's going to be in the middle. Then you have 3 oxygens. Like that. So that's minus 6, which is 18. 2, 4, 6 times 3 is 18. Now, when you draw this structure, you also have to include the charge. Otherwise, it's incomplete. But we don't have an octet yet. Can we get an octet? Well, yeah, we have 3 choices. Right? We could get an octet from this oxygen right here. Or we could have got an octet from this oxygen. Like that. Or we could have got an octet from this oxygen. There we go. Which one's right? They're all right. According to our localized electron model, Lewis dot structure has given us 3 possibilities. So which one's right? They're all right. And we can't draw them any differently because of the rules that come with the localized electron model and Lewis's procedures. So we had to invent something to fix it. And we thank Linus Pauling for that. He invented what's called resonance. These things are resonating like that. They don't stay put in one of these or the other one. They just resonate all the way. Now, there's one way to express them without doing that resonance. The problem is you don't know where to put the lone pair electrons. Because you still have to end up with 24 electrons. Right, so if we have 2, 4, 6, 8, 10, 12, 14, 16, 18, then we need 6 more electrons. 2, 4, I guess these dots would be like that. And instead of having 3 electrons assigned, 3 pairs assigned to any one of these, we spread them out in these partial bonds. But using the localized electron model doesn't allow us to do that. We have to have complete bonds, right? This is just a stopgap, a way we try to understand why it's doing it. This is the solution to the problem as it is. This is just another way of representing them, and it doesn't really help in the long run. So that was a modification to the model because it failed to explain this. So Pauling said, okay, we're going to modify the model and we're going to invent resonance. And it's still used. That concept is still used today, especially in organic chemistry. All right. So let's see. We've done carbon dioxide. Carbon monoxide is too easy. How about methanol? We could do methanol because it has 2 centers. Let's do that one. CH3 or CH3OH is methanol. All right. So we have 4 here, 6 there, and 4 for hydrogen. So that's 8, 14, okay? 14 electrons. All right, who goes in the center? Well, actually, you got 2 centers. You got a carbon center, and the way the molecule is written, this is organic chemistry. These carbons are assigned, these hydrogens are assigned to that carbon, and the bond is between this carbon and that oxygen. Like that. So once you know that, then you can put the hydrogens where they best belong. And it wouldn't make sense to put a hydrogen over here and try to bond oxygen to it because it can't tolerate that. It's only got a 1s orbital, can't make 2 bonds. So this is the only way it can work. So that's 2, 4, 6, 8, 10. That's 4 electrons left over. We have to find a place for them. Well, these already have duets. That carbon's already got an octet. So those 4 have to go as lone pairs on that oxygen. Okay, so that is your methanol molecule. Okay. All right. There will come a time when there will be more than one possible Lewis dot structure, and you can't resonate them. In other words, they're not as simple as that resonance model. So you have to decide which one is the best. Which one do we consider a valid Lewis dot structure? And to do that, we've invented this thing called formal charge. I'm going to show you how to calculate formal charge. And then the way we use formal charge is that once we've got formal charge on all the atoms in a molecule, this molecule dot structure versus this one versus that one, then we look for the one that has the smallest array of formal charges. All right. These dot structures are known as non-equivalent, whereas the resonance structures would be equivalent. All right. So how do we determine formal charge? Well, you take the on each of the atoms if it were free, right? If it were free and neutral, how many valence electrons? And then you count up the number of electrons that are assigned to it in the molecule. Subtract those. That's the formal charge. Yes. So let's do an example. Lone pair electrons belong to the individual atoms where they're located. Shared electrons are split, one electron to one electron to the other. Okay. Let's see. Come on, here we go. Let's do this one. Suppose we have this structure. And we have that one, this one, this one, and this one. Okay. I think that each one of these chlorines is going to have the same formal charge. So let's calculate those first. So how many valence electrons in the free chlorine? 7, right? 7. Then we're going to subtract the number that are assigned to it in this molecule. 1, 2, 3, 4, 5, 6, 7. Right? Because it only gets half of a bond. So each one of these is 0. Chlorine is 0 formal charge. All right. How about the oxygen? Well, the oxygen starts off with 6, doesn't it? But it has 7. So it has a formal charge of -1. How about the phosphorus? Well, the phosphorus is 5. Has 5 valence electrons. And in this one, it's assigned 1, 2, 3, 4. +1. So the phosphorus is a +1, oxygen's a -1, each of the chlorines is 0. Oops, there we go. That's how you do formal charge. Oh, and if we add up the formal charges, 0, 0, 0, -1, +1, they have to equal any charge that's on the molecule. Since this molecule is neutral, all the formal charges must add up to 0, and they do. If we had, say, a nitrate ion, then all the formal charges would have to add up to a -1. So here we have 2 non-equivalent possible structures for carbon dioxide. Right? If we do the formal charge, let's see, are we going to do that? Oh, it's expecting me to do that. I didn't animate this one. Okay, if we have this possibility, and that has an octet, 2,4,6,8, 2,4,6,8, 2,4,6,8, we're good. And if we have, let's see, this one, and a pair there, and 3 pair there for the U. Yeah. So the formal charge here would be oxygen has 4 to begin with, and we're assigning 1, 2, 3, 4 equals 0. So that oxygen is 0. That carbon is 0. This oxygen starts with 6, right? We have 2, 4, 5, 6. -6 equals 0. And this one would be 0 also. So all of them are 0. That's good. If we do this one, this carbon is 4 - 4 again, which would be 0. Right? 1, 2, 3, 4 minus subtracted from 4 is 0. This oxygen has 6 minus 2, 3, 4, 5. -5 equals +1. This one is 6 minus 1, 2, 3, 4, 5, 6, 7. 7 is minus 1. Now, it does obey the rule. If you add them all together, you get 0. But all of these are 0 formal charge, and these are 0 plus 1 minus 1. That one's better than this one because it has more of the lower formal charges than this one does. So that's how you break the tie. Okay. Now this, let's see, I keep forgetting if we've done, hold on a second. No, we get that next semester. This is a bookkeeping scheme. It doesn't say that these have a charge of 0, 0, or 0, or these have a charge of plus 1, 0, minus 1. It's just a way of assigning an imbalance, if available, an imbalance in electron distribution that would tell us one structure is less stable than the other. This structure is more stable than that one. It doesn't say that this one has a minus 1 charge and that one has a plus 1 charge. It just says that because of this calculation, that one is more stable. That one's the preferred one. So we don't want to use formal charge as a true charge. That would be overextending the model. Okay, now I said I was going to get to this eventually. The VS-EPR model. And that's derived from the local, it's companion to the localized electron model or the valence bond theory. So the VS-EPR model, VS-EPR, is valence, shell, electron pair repulsion. And all that's saying is that when you have a constructed Lewis dot structure, the electrons around any chosen central atom, if it's a very simple atom where you only have one central atom in the molecule, then it's easier to say this. But all the atoms attached to it and any lone pair electrons that are attached to that central atom try to get as far from each other as possible. They try to minimize the repulsive forces by spreading themselves out. That's the VS-EPR model. The VS-EPR model is companion to the localized electron model because this model helps us predict the geometry of our molecules. Right. And by minimizing the electron pair repulsions, we put a lot of distance, as much distance as possible between the electron pairs, whether they're lone pairs or in bonding. We put as much distance between them as possible in a regular geometric structure. Now, if you have a large molecule, you may have more than one center of symmetry. So you may, on one end of the molecule, you might have a tetrahedral symmetry, and on the other end, you might have a linear, and you may have a trigonal planar in between somewhere. So you can have more than one in large molecules. But we're going to start off with simple molecules. Okay, come on. There we go. I mentioned this one earlier. A linear structure simply has something in the middle and then something on either end. It could be a Y, it could be a Z, it doesn't matter. And the bond angle here is 180 degrees. This is linear. Trigonal planar is like we have the X in the middle and we have these Y's there. So it's in a plane and the bond angle is 120 degrees. Then we have tetrahedral, where we have 5 members with X in the middle. We have a Y up here. We have a Y down here, a Y down here, and we have a Y in the back. Right, so we have that triangular base, and we form this tetrahedron, and the bond angle is 109.5 degrees. You can ask your math teacher to derive that. I'm too far removed from math to remember how to do it. There are others, and we'll present those as the need arises. Okay, let's make room. So the steps for using the VSEP model are, first you draw the Lewis dot structure. You have to do that first. Then you count the number of electron pairs. And by that, we also mean groups. And I'll show you what I mean in just a second. Around the central atom. And that includes lone pairs. And then we apply a regular geometric structure to that part of the molecule that places the bonding and lone pair electrons as far apart from one another as possible. That gives you the electronic structure. Then if we want to know the geometric structure, the atomic structure of the molecule, then we just sort of cover up the lone pairs on the central atom and say what's left over. So that's how we're going to work this. Let's do it this way. Let's form a table. And let's see. Let's say in our first column here, we're going to have electron groups. The reason I say that is when we've got a double bond, we count that as a single group. We don't count it as 2 pairs for the purpose of the model. So we have the number of electron groups around the central atom. Then we have, let's see, the electronic geometry. And we have the molecular geometry. Okay, and then we might have some examples. Okay, so if we have something like well, if you have one electron group, say I don't know, like this, it's linear. That's it. It can't be anything else. So we're not going to use just one electron. If you have two electron groups, like HCN. We drew HCN earlier, right? It looked like this, HCN, like that. And we want to know the geometry. The central atom is carbon. It has 2 groups around it. Okay? So 2 groups means linear. And since there are no lone pairs to cover up and see what's left over, it also has a linear geometry here. And the bond angle, I left that out, bond angle. put it in here. Bond angle is 180 degrees. Okay. Now, what about pH 3? Let's draw that one. So phosphorus has 5, 5, 6, 7, 8 electrons. So 2, 4, 6, 8. Okay. That's not a good one. I don't think. One, 2, 3, 5, 8. Yeah, that one's going to be a mess. So let's do let's see. I can't think of a good one. I need a trigonal planar. Oh, boron trihydride. We did this one before. Boron trihydride. Like that. Okay. It has 3 groups around the central atom, which means it's trigonal planar. And the bond angles are 120 degrees. Molecular geometry is also trigonal planar. Because there are no lone pairs. Oh, I know. Yeah, okay. Next example, water. H2O. We draw H2O's Lewis dot structure. We would do like this, like that, but that has 4 groups around it, right? So that means 4, it means tetrahedral. And that's the electronic structure. But if we cover these 2 up, if we put it in a tetrahedron, like oxygen here, we have a lone pair there, a lone pair in the back, and then we have hydrogen, hydrogen here, hydrogen here. We get this tetrahedral electronic structure. Well, if we cover up those lone pairs, we get a bent molecule. Your book might call it angular. I like bent. So to fill in our table, we would just do this, like that, and like that. That gives us a bent molecule. Now the tetrahedron has what angle? 109.5. That's nominal for a tetrahedron. But when you have lone pairs that are not confined by a bond, they tend to balloon. And if these things balloon, they're going to compress these down like that, which means the actual is probably about 107 degrees, something in that neighborhood. Okay. So let's do pH 3 now. It has 4 electron groups, which means it's tetrahedron electronically. pH 3, let's do the pH 3. P, H, 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 H. And we had the lone pair here, right? So it's tetrahedron electronically. But if we cover this one up and we put P here, like that, and we put an H in the back, an H out here, and an H out here, we have this trigonal base. And we cover this one up, what do we have left? We have a trigonal pyramid. So the molecular is trigonal pyramid. That's when we have one lone pair. Oh, that's right. Let's see. Lone pairs. I knew I left one out. Lone pairs. This one has no lone pairs around the central atom. This one has lone pairs. This one has two lone pairs. This one has one lone pair. And that gives us a trigonal pyramid. Okay. Let's see who's next. SF4. All right. Here we go. This is better. We'll come back to those others. So here's a representation of the number of electron pairs, 2, 3, 4. We've got so far 2, 3, 4. Tetrahedral. If we have 5, here, trigonal bipyramidal. So if we have 5 electron pairs, and then it's trigonal bipyramid. Now, what are the bond angles? Well, you notice that if each of those positions is occupied by an atom, each of those lobes has an atom attached to it, then you could have 90 degrees between the top one and one on the square, or you could have 90 degrees between two on the square, or the one they left out is what's the bond angle between the top apex and the bottom apex? 180 degrees. So the bond angles here could be 90 or 180 degrees. Okay, that's if all the positions are occupied and no lone pairs, in which case we would have trigonal bipyramid as well. I don't have an example yet. What would happen if in this trigonal bipyramid we did have one lone pair? Where would it go? Well, we had to resort to research to find out where it would go. We might logically think it would go on one of those apexes, but it doesn't. In fact, it goes on the square. So the square then would be whatever's here, and then you would have here, 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 and here, like that. And if you turn it on its side like this, turn it like that, you have a seesaw. So if we have 5 here and one lone pair, then you get a seesaw. If you have 2 lone pairs, I think, let's see. Okay, that's the tetrahedral. Here we go. Oh, excuse me. Trigonal bipyramid. Yeah, that's 1, 2, 3, 4, 5. That's right. Trigonal bipyramid. If you have one lone pair, you get a seesaw. Another lone pair would be located on that central atom in the triangle. That would leave you with a T-shape. So 2 lone pairs would still be trigonal bipyramid electronic, but this would be T-shape if you have 2 lone pairs. Now, if you had 3 lone pairs, that would also go on here, and then you'd end up with a linear molecule. Okay. So this one could still have 90 and 180. This one could only have 180. Okay. The last one, okay. It doesn't have that one. I'll have to show you that one extra. But let's go back and see if we need to pick up any of these others. There's your sea salt, SF4. SF4 is a sea salt. Give you a sea salt. So what it must have one lone pair around the sulfur to give you a sea salt. 120. Oh, I'm sorry. I messed up. It's 94 notes. No, it's not 90. If you go from top to bottom, it's 180. So you can still have 180 for each one of these as possibles. But these two could have 120 because you have that triangle in the middle. Yeah, 120, 120, 120 is 360. These two could still have 120 degree, but this one doesn't have any in the middle, so it's only 180. How does it say 90? Oh, yeah. It could have 90. Three possibilities. Not this one. Or trigonal bipyramid. Okay. Let's see. What do we got here? What's O3? Ozone. Ozone. If it's in the upper atmosphere, in the stratosphere, it's good. It absorbs ultraviolet radiation. If it's down here where we breathe it, there's a limit. You can tolerate a little bit of it, but too much of it will damage your lungs. I know there are devices that you can put in your house or in your HVAC system that emit ozone. And what it does is it not only kills bacteria and molds, but it also destroys odor molecules. When the laser printers first came out a long time ago, they had a bad habit of making lots of ozone. So the company, IBM, I think was the first. The companies decided until we can figure out how to reduce the ozone, we would put these little activated charcoal, activated carbon packs in there where the origin was, and it would suck up all that ozone. So they were good as long as they lasted, but you'd have to replace them periodically. Krypton tetrafluoride. Let's do that. Okay. Krypton's 8, right? It's a noble gas. And 4 times 7 is 28. So that's 36 electrons. Okay. Krypton's in the middle. You got 4 fluorines. 2, 4, 6, 8. 28. So we put 6 around each one of these times 4 is 24. Equals 4 electrons. That has to go here and here. All right. Let's see. I'm going to have to erase some to make room. Everybody got these? Okay. Let's come down to, let's take it down to 4. Okay. Now, how many do we have around the central atom? 6. 6 electron groups around the central atom. And no lone pairs. The electronic geometry of this is the octahedron. So it would look something like, draw your square in the middle, and then you have an apex up here and down here. So krypton will be there. We have, and the fluorines would go on the square. This has been determined experimentally also. The lone pairs, the two lone pairs go up here and down here. All right, so if you don't have any lone pairs, then of course you have that octahedron. And the angles would be, you could have 90 degrees here, or you could have 90 degrees here, or you could have 180. So it's 90 and 180 possible. Okay, our example here has two lone pairs. So the octahedron then gives rise to square planar. And that's krypton tetrafluoride. It's a possibility. Okay, a molecule, this is a concept check. A molecule that has polar bonds will always be polar. No, that's only one factor. If it has polar bonds, then you need to know the geometry. Now, these bonds are going to be polar because fluorine is the most electronegative and is pulling from krypton. But they're all pointing in balanced directions with equal magnitudes. This is a non-polar molecule because of its geometry. All right. Draw CO2. Does CO2 contain polar bonds? Yes. Is the molecule polar or non-polar? We did CO2 before. It's a linear molecule, carbon, oxygen. Equally polar bonds, opposite direction cancels out. Carbon dioxide is a non-polar molecule. Lone pairs make a molecule polar. Not necessarily. We've got a lone pair here and a lone pair here. They're opposite one another. They cancel out. So that's another false statement. Xenon tetrafluoride. Well, that's going to be like this one. All right. So let me see. We've got that and that. Okay. Okay, here's the problem as presented. When phosphorus reacts with chlorine gas, the compound phosphorus pentachloride is formed. Okay, that's it. In the gaseous and the liquid states, this substance consists of PCl5 molecules. But in the solid state, it consists of PCl4 plus and PCl6 minus ions. All right. So what's the geometric structure for PCl5, PCl4 plus, and PCl6 minus? I think that's on the next page. PCl5 is a trigonal bipyramid, which means it has 5 electron groups. PCl5. Maybe if we draw this one, then we can just modify it as we go from one to the next. So PCl5. This is working any better. Phosphorus is 5. Yes. 5 and 7 times 5 or 8 times 5 is 40. We have 40 electrons. Okay. Phosphorus in the middle. 1, 2, 3, 4, 5 fluorines. 2, 4, 6, 8, 10. So now we're left with 30. 2, 4, 6 times 5 is 30. Use them all up. So that's why this is, it has 5 groups. It's a trigonal bipyramid. Okay. Let's see. Oh, there it is. Okay, so what's the next one? PCl4? 4 plus. PCl 4 plus.
So if we do PCl4, let's do the whole thing. PCl4 plus, we have 5, plus 4 times 7 is 28, minus 1 for that charge. So that's 33 minus 1 is 32. Okay. P 1, 2, 3, 4. 2, 4, 6, 8. 24. 6 times 4 is 24. And we have to keep the charge.
So is this one tetrahedral? Okay. There it is. And PCl5 minus is the next one, right? Oh, PCl6 minus. Yeah, PCl6 minus.
Okay. So we have 5 plus 7 times 6 plus 1 for that charge. So that's 42, 47, 48 electrons. All right, so P 1, 2, 3, 4, 5, 6. Two, 4, 6, 8, 10, 12. And it's 36. We put 6 around each one of them times 6 is 36. So that uses them all up. But this phosphorus exceeds the output. Okay, so if we have 6 groups, that's octahedral, right? So it'd be this, that.
And we have an octahedral molecule. Like that. Okay. Okay, we didn't expect the noble gases, since they have filled orbitals, to be chemically reactive. And the smaller noble gases are not chemically reactive. Helium and neon are not chemically reactive at all. But the larger ones, apparently the electrons are so far away from and shielded from the nucleus that they're available to react. A few argons. Most of them are krypton and xenon molecules. Okay, this particular one, xenon tetrafluoride, was formed, and we did one that was with krypton. The xenon tetrafluoride is going to be the same. Xenon tetrafluoride should have like that, with fluorines here, fluorine here, fluorine here, there, and octets all around the fluorines. And then you have a lone pair here. So the lone pair would be up here and down here, which would give you your octahedron. And since the lone pairs are at the apex, the molecular structure is square planar. And since these bonds are polar, but they're balanced, they cancel out, this molecule is nonpolar. Like that. Let's see, like that. That's a possibility. We're looking at the left-hand side, making a seesaw out of it. If that were the case, if that were the left-hand side were the case, then this molecule would be polar. And you could measure that in the laboratory. But what we measure is a nonpolar molecule. So the square planar is the only one that works. Right. So actually, we deduced that it's nonpolar, but actually it was proposed, and then the laboratory confirmed that it was this and not the other one. Sometimes when you're studying a new subject, it doesn't matter if it's chemistry or some other science. You have a tendency, since these projects have already been determined, they've already been run, they've already proven their points, that you just learn the points and you work the other direction. When sometimes it's more instructive to look at the experiment that gave you the points, and then maybe it'll stick better. Because you know the people that are working on this project are not going to forget it. Okay, we're getting close. Okay. Those lone pairs sticking out above and below do need more room, which is what we would expect for the trigonal bipyramid, but it doesn't work that way, right? So we could have predicted wrongly for the trigonal bipyramid with its lone pairs, and correctly for the octahedral with its lone pairs. So you just have to go with the evidence. Okay, let's see. Has no dipole moment. Yep. That confirms the square planar geometry.